Last time, did I actually write down the summary of like what the solutions look like for different characteristic equations?
No, you gave that lecture.
I should probably write that down. So just to close out 3.4, not anything new, it's just a summary of all the situations. So, let's continue. So, given zero ABC constants, zero. What is the characteristic equation for this differential equation? AR squared plus BR plus C equals 0. And we assume the solution, well, this would probably came before this step or whatever, is, what's the form for the solution?
C1.
No, the basic
E or E to the RT.
e to the RT. Right? So if you make that assumption, this is what you end up with, and you have several situations. There's one, the case where you have R1 not equal R2, R2 distinct roots. Then what's the general solution in this case?
C1 E to the RT. E to the RT.
The second case, if both roots are the same, say R, then Y equals right, which we can derive by reduction of order. The third case, where R is equal to R1 and 2 is equal to A plus or minus IB, that is complex roots. Then Y is equal to C1 okay, know this. Double underline, highlighted, red font, 72 size font. Know that, like you know your own name, right? So I say about any one of these, and you take more than 2 seconds to tell me what the answer is, you're not studying hard enough, okay? But this you should just know. You have a second order linear differential equation with constant coefficients. This is what you assume the solution looks like. You will obtain this equation. You can usually just, after this, just write down this equation and solve it. It's a quadratic. You should be able to factor it. If not factor it, use quadratic formula or whatever. And in these three, you will have 3 possible situations. You get 2 distinct answers, that's your solution. If you get a repeated root, that's the solution. If you get a complex root, that's the solution. This is something you should just know. Okay. Now, we're going to talk about the non-homogeneous case. We're going to deal with it with the method of undetermined coefficients, it's called. So, again, let's start a little bit more generally. given y, let's do the plus by prime plus cy equals g of t. Cool. It actually works in more generally, so I should probably do this. Okay, p of t, q of t, g of t, where we're assuming the nice situation, these are all continuous on some open interval, and that's the interval we care about. P, q, g are continuous. Interval I, your g of t is not identically 0, which means it's just a general function that's not always 0, right? So we're not in the homogeneous case anymore, right? This is how we deal with a homogeneous case. There are really 3 possibilities when we have constant coefficients, right? Suppose we don't have that, then so I'm going to name these because I'm going to be referring to them. Call this equation 1. Call this equation 2. And the corresponding. Or it's called the associated sometimes. Associated homogeneous equation. All right, so it's basically the same equation, but I put a 0 here. We call that the corresponding homogeneous equation. Assume the solution to 2 is, let me call it YH, or this homogeneous solution, C1Y1 plus C2Y2. Now, the question is, what does the solution to 1 look like? This one we sort of know how to do it. Not every case for general functions p and q, but for the situation with constants and a couple of other situations we know. But what if it's not 0 on that side? How do we know what the solutions look like? Well, here's how we're going to know. Let y be a general solution. One. Let y sub p be a particular solution to 1. Right? Any specific solution that we can get our hands on, it doesn't matter which one. Any specific solution. Note that something weird happens when I take y minus yp and plug it into this differential equation, into this one. So y minus yp double prime plus p times y minus yp prime plus q times y minus yp equals 0. Equals, let's not assume it's 0. Let's just plug it into this differential equation and see what we get. This guy actually simplifies to, I can write this as y double prime plus py prime plus qy, and this guy minus right? What's this guy? Y is the general solution to 1. So if I have y double prime plus py prime plus qy, what do I get? G. Right? 1 is the differential equation where there's a G on the right side, which means if I plug in any solution for the y's, the result will be G. What is the solution to this one? What is that? Yp happens to be a particular solution to that equation. So what would be the result if I plug it into the differential equation? It's not a trick question. It's probably what you're thinking. Right? Yp solves this equation. So if I plug in Yp here, Yp here, Yp here, what is the result? G. I'm not trying to trick you, guys. Don't worry. Okay. So G minus G is 0.
GP, no?
No, G.
GP.
Yeah. Yp is just a solution to this, right?
Ah.
So if I plug it into that, it should give me that answer. Right? So it's 0. What does that mean? This means that y minus yp solves the homogeneous equation. If I plug in y minus yp into this differential equation, the result is 0, which means it actually solves this one. Which means, I forget the theorem number, theorem 2 point, you won't need to know what the theorem number is. Theorem 3.2.4. Theorem 3.2.4 gives that we can write this is a theorem that said if we have, this is the solution to the homogeneous equation, every solution to the homogeneous equation can be written in this form, right? This is a solution to the homogeneous equation. It means that this I can write in that form. Right? It's possible to find constants C1 and C2 so that this is true. But this guy is just YH, the homogeneous solution. That means that Y, the general solution, will just be the sum of the homogeneous solution plus the sum of any particular solution. So if you have the non-homogeneous case, once you know how to solve the homogeneous case, if you take that and add it to any particular solution to the general equation with g of t on one side, which I erased, this is what the solution would look like. You need to be able to find the homogeneous first, which is why 3.5 is still very important to us in this section, right? But then you have the added burden of you have to find some particular solution. So, yeah, in order to find the solution to this differential equation, you have to be able to find the solution to the differential equation. Sounds circular, but it's actually not. We actually have a method where we can get our hands on a particular solution. It's called the method of undetermined coefficients. There are a couple methods, but in this section, that's the method we're going to look at. Now, there are some caveats to this. So, let me put it under remarks. I usually never put remarks. One, one thing is important. We need each term in yp to be linearly independent to each term in yh. Why is that important? Well, if something in my particular is also a homogeneous solution, then when I plug it in, that part is just going to die. It's not really going to give me any information. Right? And if the particular solution I pick happens to be exactly the homogeneous solution, when I plug it into my differential equation, I'm just going to end up with like 0 equals 0. I'm not going to give any information because everything will die. The guys in YH just die when you plug them into the differential equation. They turn into zeros. So we don't want that. So we want to make sure that whatever terms we're picking for this guy, they don't show up over here because they wouldn't help us, right? They'll just turn into 0 when we plug them in. So we need to make sure we have linear independence. Recall, you can get this by what we learned from reduction of order, multiplying by t. As many times as we need to. It turns out there are cases where we'll have to do it more than once. Right. When I do some examples, that will be more clear what I mean by that. Another remark. Any YP will work, remember that. So how do we find a solution? Try to find the easiest one. What is the easiest one? This will be, in theory, the one similar in terms of linear independence to the G, but not similar to YH. This is sort of going back to when we sort of figured out why did we want to assume it was exponential? Well, just because of the similarity of the derivatives, right? I know if I differentiate the exponential, I keep getting the exponential back, so it sort of made sense. We're going to sort of apply the same idea here. We just want to plug in something that's similar to the right side so that when we work everything out, we should get the right side, right? That's sort of the idea. In doing so, we will obtain similar means it can differ by a constant factor, right? So in doing so, we will get arbitrary coefficients that we must determine. Right. So basically you assume it will have this form, you'll have these constant factors that you don't really know what they are. They're undetermined coefficients, which is why the method is called that. So what we're going to have to do, we're going to have to determine what these coefficients are. And basically once we can do that, we can get the solution. Process. We're almost done with the theory behind this. We're just define these. It's called, you guessed it, the method of undetermined coefficients. It is not a universal technique. There are cases where this method doesn't work, but there are also cases where it does, and we're going to talk about those cases. And if we have time, we'll talk about cases where it doesn't work and what else we can do. Basically, the method relies on this. Choose YP to be the form based on the following chart. Space for the chart. Just to be safe, I'll write it over here. So there are certain forms that are very nice to use with undetermined coefficients, and they're the following. So let's say you have the form of G, and the question is, what do we pick for the form of yp? So let's say the right side of your equation looks like in the chart, I'm going to use a notation. Ps of t is some specific polynomial. Pn of degree n. And I'm going to do Pn equals the general polynomial. Okay, so let's say the right side of your equation is actually some specific polynomial, right? What's a form similar to a polynomial? Well, another polynomial, right? It'll be the general one, right? Some general polynomial. So also, I might have to multiply this by t to the k. I'm going to define what k is. So an example here would be, let's say your right side of your equation is x squared plus 1, right? What would you assume that yp looks like? T squared plus 1, since we're using t. We'd assume that yp would look like at squared plus bt plus c, right? So this is a second degree polynomial. So the form I'm going to assume for yp is the general second degree polynomial, right? Now if that happens to, if any one of these terms happen to be in the homogeneous solution, what we're going to do to fix that is multiply by t a certain amount of times until we get rid of that similarity, right? So that's the first case. There's another case that's very nice. Suppose you have a polynomial times e to the at. Then you're going to assume yp is the general polynomial times e to the at. And then again you multiply by t some amount of times to kill any redundancies that may or may not exist. So example, if your right side is t e to the t, over here you would choose at plus b times e to the t. T is a first degree polynomial. You write down the general first degree polynomial times e to the t. Right? And then, just in case there's redundancy, you'd multiply by t's to kill anything that looks like a homogeneous solution. Another case. You have some particular polynomial times e to the at, and that is times either sine or cosine. Right? Even if you have only one of them, you must assume that both of them will show up. So for example, we here will have p of Pn of t e to the at cosine bt plus, that's one general polynomial, plus some other general polynomial e to the at sine bt. And then that whole thing we will multiply by t to the k. Let's do an example. Yes.
So for sine bt, we multiply with sine bt to the other part?
No, does it say it can be either or?
Right, but like if it's the first one, then which one is it for the other one?
I'm not sure.
Like if it's the first one for the form of
Yeah.
gt, that one, which one is going to be for the...
That's always the form for both of them.
Oh, okay.
Yeah. So, example, let's say your g of t is equal to 2 sine t, right? Then what you would pick for yp would be a sine t. Well, they usually put the cosine first, there's no particular reason. Plus b sine t. And then you multiply that by t to the k as necessary. Right? Once a sine or a cosine shows up, you have to put both of them. Because when you start taking derivatives of sine and cosine, they turn into each other, right? So you want to make sure that you cover all your bases, right? Or what if your g of t is equal to t sine t? What would you assume yp looks like? Well, this is a general first degree this is a particular first degree polynomial. I must put a general first degree polynomial times cosine plus some other general first degree polynomial times sine. Even if it's just only the sine that shows up, you have to put both this cosine and the sine. Because when you start taking derivatives, they'll change, right? The y prime would be a cosine, while the y double prime would also be a sine. So once you have sine or cosine, both sines and cosines will show up in your differential equation. So you have to assume that that's the general form that you will take on. Right? Or if you have g of t equals 2 e to the t sine 3t. Let's pretend that's your right side. What would you assume yp looks like? This is a general 0 degree, which means constant polynomial. So what does the general form for that look like? Just a constant, a. e to the t cosine 3t plus b e to the t sine 3t. We're sort of seeing how this works. We're just taking all the pieces and making them as general as they can possibly be, and then put those in a general form. These guys here that show up, this a and this b, those are the undetermined coefficients that we're going to have to figure out what they are. Let me write down specifically.
Hey, how about the p and 2? This is still a plus.
Huh? Right here?
Yeah, this is plus in front of it.
Yeah, there's a plus. Right? It's this plus that. Yeah. Okay, so note k is the number of times you must multiply by t to ensure no term in your yp looks like the term in your yh, right? Remember, it's very important that these are not similar, because we end up with redundancy and nonsense. All right, let's do some examples. Bunch of examples. Hopefully we can get through all of them today. We're not going to go all the way with all of them, just at least try to set up what yp would look like, and then I'll do a problem where we go through the whole process, and then hopefully you'll get it by then. Trust me, it's one thing, it looks complicated now when you're first saying, oh, holy crap, what is all this? But when you get into it, it's going to be something that's, oh yeah, it's going to be straightforward. Examples. Find the form At this point, I don't want you to solve for the arbitrary constants just yet. Just try to figure out what the solution would look like in general. Don't solve arbitrary constants. Here's the first one. Not find the form for YP. Find the form for, let's do it a little bigger, the general solution. So A, let's say we had y double prime plus 4y prime plus 3y equals e to the t. Can I erase this? The form? What does the general solution to that look like? And what if I gave you the same thing basically, but I changed the right side this time to be minus t? You'll actually deal with these two differently. Not significantly differently, but it's different enough. How would I find the general solution here? Well, the trick is first, find YH, because remember, we have to choose our YP to not be redundant with the YH, so it would be good to know what YH looks like first. How would I find the homogeneous solution to this? Right, so you pretend for a second this is 0. How would you solve that? So what would we get? That thing I told you at the beginning to know. Tell me, I have numbers here. Tell me
R
what.
squared plus 4R.
R squared plus 4R plus 3 equals 0. How do we solve that?
R plus 1, R plus 3.
R plus 1 times R plus 3. So we get R equals minus 1 or R equals minus 3. So the homogeneous solution is C1 e to the minus t plus C2 e to the minus 3t. Right? This means my YP, what do I want to do? I want the YP to look like this, but not like that. But we're okay. This is e to the minus 3t. This is e to the minus t, e to the minus 3t. That's e to the positive 1t. It doesn't look the same, so I can pretty much ignore this and just choose, oh, a e to the t. Which means, do I have space? Which means, general form solution for my y would be c1 e to the minus t plus c2 e to the minus 3t plus a e to the t. My general solution will have this one. So now, right? So you're given this, it's the non-homogeneous case. Pretend it's homogeneous for a second, find the homogeneous solution. Boom. Then you want to choose a function that looks like this, is similar to this, but is not similar to anyone here. But once the power of e is different, it's automatically not similar to itself. So we can, none of these guys pose a problem, so we just pick something that's similar to that, and we're done. And when we add these two, that gives us the general solution. Right? Let's say the situation were different. Let's say slightly different. It was an e to the minus t over here. Right? Again, remember, YH is C1 e to the minus t plus C2 e to the minus 3t. Now what do you notice? It's similar. You see, this term here is similar to that. They're both e to the minus t's. They're both a constant times e to the minus t. We don't want that. So what are we going to do? So we would start out by saying, okay, to be similar to g, we have to be that. But that already looks like this. So what do? Multiply by t. I only need to multiply by 1t because now I'm not similar to anyone else. So the general solution will be c1 e to the minus t plus c2 e to the minus 3t plus at e to the minus t. Let's do another one. Let me skip those two because I want to emphasize what I just emphasized a little more. So let's skip C and D. Let's go to E. We'll come back to C and D. Let me call this C. Y double prime minus 2y prime plus y equals e to the t. Secondly, I'm going to want y double prime minus 2y prime plus y equals t e to the t. And whatever that is, y double prime minus 2y prime plus y equals t squared e to the t. All right, what's the first thing to do?
This one.
What's r?
1.
All right, you just get r minus 1 all squared equals 0, which means you have a repeated root of 1, which means your homogeneous solution looks like what?
C1 e to the t plus C2 t e to the t.
All right, so now, knowing that, we want to pick our yp, right? Now yp has to look like e to the t, right? General form, a e to the t.
A t e to the t.
So now we're like, that looks like this. Let's multiply by a t.
So
And now you're like, now that looks like this. Multiply by t again, right? You multiply by t as many times as you need to not look like anyone here. You get the idea? So you start by looking like this, and then you look here and like, does anyone look the same? If anyone looks the same, multiply by t. Because that kills, they're not linear dependent anymore once you do that. And if it looks like someone else, multiply by t again. Looks like someone else, multiply by t again. You just keep doing it.
So basically just make it more than the exponent of t with 1, right?
Yeah, like, just try to make it more general. So we have, this means your y would be, in this case, c1 e to the t plus c2 t e to the t plus at squared e to the t. And there's going to be a method of how we're going to find what that a has to be. What about this one? It's the same on the left side as this. So, you know, we know that yh is c1 e to the t plus c2 e to the c2t e to the t. So now our yp, what would yp look like here?
AT
squared.
squared?
No.
No, AT plus.
Make it look like g.
Yeah,
I have a particular first degree polynomial here.
so plus B
Plus b
times
e to the t. Now I'm going to check, does that look like anyone in my homogeneous solution?
Yeah.
Yeah, when I multiply out, at e to the t is going to look like that guy. Multiply by a t. Are we okay now?
Repeat again, YP.
Huh?
Repeat YP again.
Remember, we start out by making yp look like g.
Oh.
In this case, g is a first degree polynomial times e to the t. So our yp should look like a first degree polynomial times e to the t. But I make it general, right? So I go, that's the general form of a first degree polynomial, a linear polynomial, times e to the t. And now I want to check, does anyone here look like anyone there? And the answer is yes. At times this looks like that. So I multiply by t.
We're still not good.
We're still not good, because if I take t and expand, get bt times e to the t, it still looks like that. Multiply by t again. Now are we out of the woods? We'd have at cubed e to the t and bt squared e to the t, which doesn't look like any of those guys. So now we're good. This means that our y would look like c1 e to the t plus c2 t e to the t plus t squared a t plus b e to the t.
Where are you in the t plus b?
The general first degree, right? If I ask you for what does a linear polynomial look like, it would be, you know, like y equals mx plus b. That's the form. You want to put the most general form. So let's do this one. Let's see. So again, it's the same left-hand side, so our homogeneous is again the same. Now, what is yp, right? So we look at g. Notice g is a second degree linear polynomial, second degree polynomial times e to the t. So we look at this t squared, it's like a quadratic. What is the general form of a quadratic? Right. At squared plus bt plus c times e to the t. Right? And now we do our check. Does anyone here look like anyone there? Yes, the t e to the t, and we have a constant e to the t. It looks like those guys. Multiply by t. This would be t cubed e to the t, t squared e to the t. That would be t e to the t. Multiply by t again. T to the fourth e to the t, t to the cubed e to the t, t to the squared e to the t. We're good. Right? They don't look like anyone here. So in this case, your general solution would be c1 e to the t plus c2 t e to the t plus t squared at squared plus bt plus c. So you see, just by changing the right side, you can actually get very different situations because you have to make sure that there are no redundancies. And you have to make sure that the right side that you pick starts out by looking like this one, of similar form, but you have to make sure that there are no overlaps between that and the homogeneous. Right? That's the whole. Yeah.
Does it matter where your k is as long as it's not redundant? Like if you multiplied it by another t?
Yeah, it could work in general, but remember, any yp will work, so find the easiest one, right? In general, dealing with something with t cubed is going to be harder than dealing with t squared. So we just stop, we don't do it more than we have to. But technically, if you did put a t cubed here, you would be able to find some solution in theory a lot of the time. But this is good enough.
So
right?
that if you ask for a general solution in the exam, I could just put a high number to make sure I'm correct?
No, you choose wisely. Because then you put like t to the 1,000 times this. Then he's just trying to get away with not thinking. No. All right, so more examples. Just setting them up. We'll deal with actually solving these guys in general. EF. Let me backtrack here because I skipped one. Y double prime plus y equals x e to the x. Y double prime plus y equals 3 sine x. Can I erase this? Did you guys get this? H. this one? Okay, and just to warn you, we are now officially in the neighborhood of the problems in 391 that can get incredibly long. So if you have any issues with algebra, you know you have a weakness with algebra, now's the time to fix it. You work on that this weekend. Because finding these A, B's, and C's, a lot of algebra. It's going to feel very similar to integration by partial fractions. We're going to have to set up like a bunch of equations to solve for them, and then you're going to plug them back in, and yeah, it's going to be, just so you know.
We're going to sleep with 500 sheets of paper just to be ready for it.
It's possible. And if you choose, it's worse if you choose the wrong form for YP. So if you want to be like, oh, you're going to be smart, oh, t to the 1,000, you're making your life harder, right? So you multiply by just what you need to make things work. And it makes your life easier. We actually started here. Okay, y dou prime plus y equals x e to the x. What's the first step?
R squared plus R equals 0.
What is r?
Plus or minus 1.
Plus or minus?
1.
No. I. We have complex roots here. So what does that mean yh look like?
Euler. E to the T.
C1.
C1
C1 cosine C plus C times sine C. Yeah, remember that summary? Make sure you know that next time. Just know it. Like this is 0, A is 0, B is 1. So you have A plus or minus B, I. You just plug into the general form. Okay, so now that we have our YH, it turns out that here it's cosine and sine. Doesn't look anything like that, so you can just choose, well, technically, I'm using x as the independent variable here. Be consistent. So YP would just look like, what would YP look like?
AX plus B.
AX plus B, e to the x, right? And it obviously doesn't look like any of those, so the general solution will have the form C1 cosine x plus C2 sine x plus AX plus B e to the x. Okay, this one. Again, same left side as this one. I did that intentionally just for you to see how things can be different. So here, we already know what YH is. We solve for it here. C1 cosine x plus C2 sine x. Now, what does the YP look like? Yeah?
What was it? A cosine t plus b sine t.
Right, you start out by making it look similar to this. Now remember, once you have a sine or a cosine, you have to put both of them. So I put A cosine t plus B sine cosine x plus B sine x.
Oh.
Right? Are there any overlaps?
YH.
It's
So
an exact overlap. So
multiply it by t.
multiply this whole thing by,
Oh, x.
we're using x here. And now we're good. So the general solution is C1 cosine x plus C2 sine x plus x cosine x plus B sine x. So that's what we're seeing here. The general solution is always the sum of the homogeneous solution plus any particular solution that we can find. And it turns out we will be able to determine the big A and B such that this thing actually solves that. And that's the method of undetermined coefficients. So we'll get there eventually. This one? What do we do?
R squared minus R minus 6.
Can you solve that?
R minus 3, R plus 3.
R minus 3, R plus 2. So we have R equals 3 or R equals minus 2. This means your homogeneous solution looks like which would mean your particular solution would look like what?
A sine 3.
Yeah, it doesn't matter which one you put first, but it's just
Isn't that similar to sine 3t?
Yeah, we have to multiply that.
does any term here look like any term there?
No.
No, these are exponentials. Those are trig functions. They're totally different. I don't have to multiply by anything. That's good enough. Y would equal c1 e to the 3t plus c2 e to the minus 2t plus a cosine. Yeah, so don't be anxious to like multiply by 2. Oh, multiply by t, like all the time. It's not always necessary. Reminds me of my calc students. They take cross products for no reason.
Really?
They're like, what do we do here? Take cross product. Like, no, you don't always. You have to do it for a reason, okay? It's not like I showed them the cross product and they were like going crazy with the cross product every time. I do the cross product. No. Okay. So same time, you don't always multiply by t. You check, you look. Is anything similar? If no, you're good. Don't do anything. Just put it in the sum, right? It's only if things are similar you start multiplying by t's, right? Don't be like, t squared. You don't need anything multiplying here. Right? It's already quite different. This one? How do you start?
Start for what?
R
YH?
squared minus R.
Yep. How do you solve that?
R minus 2, R plus 2R minus 1.
Plus 1.
Minus 2.
So r equals 2 or r equals minus 1, which means our homogeneous solution looks like what?
C1 equals dt plus C2 e to the negative t.
Which means our yp would look like what?
AT squared plus BT plus. No, I'm sorry. Oops.
Hmm? What would it be?
AT plus B plus B.
At plus b, right? Looks like g, which is just a linear polynomial, so it has to look like a linear polynomial. And then we have our general solution y is just c1 e to the 2t plus c2 e to the minus t plus at plus b. Two more examples in setting up. Don't know if we're going to get to actually doing this. But like for a lot of people, just getting to this part, just actually knowing what it looks like is a big problem. So I thought we'd do like tons of examples, just figuring out what the general form is. And then we'll learn how to solve them. It looks like that's going to slip into next time. So y double prime plus 2y prime plus 3y equals e to the x sine x. And Here's a question to separate the A students from the B students and below.
What F
Well,
student?
or the F students.
Plus 4
If you see it, it's not that difficult. If you don't see it, though, you'll probably be scratching your head for a while. What if I throw a sine squared here? And
that?
another problem to see. This one's just for fun. Technically, we haven't dealt with this yet, but it generalizes naturally. So sort of what you think will happen is actually going to happen. So when we get to chapter 4, we're going to talk about higher order, right? So we're not just going to focus on second order. We have third and fourth and fifth and sixth orders and all that. So let's say I ask you to K, L, try this one. Y to the fourth derivative plus 8y to the third derivative equals t squared plus e to the minus 2t plus minus e to the minus 2t cosine radical 3t. That was actually a question from a final.
My God.
Right, so this is where you're gonna be.
Is it a bonus?
Right now, this is like, oh, it was so crazy. Yeah, by the time you get to the final, you're expected to do things like that. Just so you know. Okay. This one. How do you do it? R squared plus 2r plus 3 equals 0. Doesn't factor, right? So we're going to have to bite the bullet, do the quadratic formula. What is it?
-1 plus minus I radical 2.
No.
It's -2.
Minus b plus or minus the square root of
4.
b squared minus
4ac.
4 times a times c
That's 12.
all over
2a.
2a, which is 1. So this is, I can factor out a 4, that gives me a 2, which would leave me with 1 minus 3, so that's minus 2 here, all over 2. So this really gives me minus 1 plus or minus radical 2i. Right, and so what does our YH look like?
C1,
C1,
e to the negative t,
e to the negative, well, we're using x here, e to the negative x,
cosine square root of x,
cosine squared of 2x plus
c, sine
that would be my general form of the homogeneous solution. What does y key look like? What does y key look like? Has to look similar to this, which is a constant polynomial times e to the x times sine.
A e to the x. Multiplied by, well, plus
times
No.
Cosine
Times cosine plus
b e to the x sine
b e
x.
to the x times sine. And does it overlap? No, I have e to the minus x here, and the cosine, this is in the angle, so we're completely different. And it's just safe to assume y is just the sum of these two. So it's going to be c1 e to the minus x cosine radical 2x plus c2 e to the minus x sine radical 2x plus a e to the x cosine x plus b e to the x sine x will be our general solution. You want to figure this one out?
reduction of power. You need to turn the sine squared t to 1/2 cosine 2t.
All right, this is 1/2 of, what was it?
It's 1 minus cosine 2t.
Right, so this side is really just 1/2 minus 1/2 cosine 2t. So, now if I wanted to find the homogeneous solution,
R squared plus R plus 1.
0 can't be factored, right? So we're going to have to use quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a is going to be minus a half plus or minus radical 3 over 2i, which means our yh looks like, what does the yh look like?
C1 e to the negative g over 2 plus cosine square root of g over 2 g plus c2 e to the negative plus
Okay, that's our homogeneous solution. What is our particular solution? It needs to look like this.
a plus b, a minus
A
b.
plus, so A is just a constant polynomial to look like that. What do I need to look like this?
b plus
B cosine
2t
2t
plus
C sine 2t. And nothing here overlaps, so y is going to be adding these two. So I think you're already starting to appreciate the kind of algebra mistakes that are going to be happening. I can only imagine. Grading the second test is going to be a lot of fun for me.
put on your
I'm
laptop.
being totally sarcastic, but
Just put on your laptop.
okay. Last one, sort of jumping ahead to chapter 4, but we can handle it. What do you think would happen? It's the same process. How do you think the homogeneous solution, how do you think we get to it? Right. It generalizes very naturally. What you think will happen, the fourth derivative just goes to the fourth power. Right? Plus 8r cubed equals 0. How do we solve that?
We can pull out R to the third.
R cubed is a common factor, which means R, see this 3? That's multiplicity, right? That means 0 counts for 3 solutions, right? While this one counts for 1 solution, right? A fourth order linear differential equation should have 4 roots when counting multiplicity, right? Just like how with the second order you assume it's C1y1 plus C2y2. With the fourth order you assume it's C1y1 plus C2y2 plus C3y3 plus C3y and C4y4, right? It generalizes how you, the natural way you guess it generalizes. But when we get to chapter 4, we'll talk about that. So in this case, what is YH? It would be. So this is just a constant, right? So it's just e to the 0t, which is just a constant. C1
plus C2 plus C3
plus C2 plus C3. What's the problem with this?
They all have to be some power of t.
Right. I have to multiply this one by t because it's e to the 0 plus t e to the 0 plus t squared e to the 0 plus
C to the fourth.
okay, so that is our homogeneous solution. Now, what would our particular look like? This. You take it one piece at a time. T squared.
8t squared.
Does that look like anything over here?
Yes.
Looks like this one, right?
Yeah.
Multiply by t. Does it look like anything?
Yes.
Right, because the t times this is going to give me that t squared. Multiply by another t. Does it look like anything?
C.
T squared times the c is going to give me that t squared. Multiply by another t. t cubed is what I've multiplied by. And now we are good. It doesn't look like anything. Now you move on to the second term.
Would it make sense to factor out an e to the negative 2t?
Probably not. I don't think it would. You know, it won't really make a difference. Would it make it harder? It's going to be roughly the same. It won't make a difference. So this is just a
It's the letter D.
we're up to D now, yes. And then that takes care of this guy. It doesn't look like anyone here. This is e to the minus 8. So we're done with that guy. What about this guy?
E.
E to the cosine radical 3t.
What's wrong?
Plus f e to the minus 2t sine squared 2t. And again, that doesn't look like anyone here. So now you just add these all up. Y general is going to be c1 plus c2t plus c3 t squared plus c4 e to the minus t 8t plus t times at squared plus bt plus c plus d e to the minus 2t plus
And that's one you said was on a final, right?
This was on a final. Yes.
How long does it take to get the coefficients on something this long?
Well, you remember how you'd find these coefficients? You'd find the derivatives and then you'd plug them all in, and then you'd solve for them. Same thing.
So they have to.
You're going to find all these derivatives. You're going to plug them into the differential equation. Then you're going to set it equal to both sides, and then you're going to find them that way.
In this finals, they had to do it. They had to do it for this problem.
My God! In this question was like part B of some other question. and
Part
actually
B of
just write this
something?
down. They never made you solve for it. They just say write down the general formula.
Okay, I was like software. I was like, are you math professors crazy or something?
Oh yeah.
I'm kind of scared if we have to do that. I thought physics was supposed to do it.
That is the exam.
That is.